and I ask you to start presenting it, please. Okay, it's no problem. So, Rebecca, please. What happened? I don't see anything. There should be some problem. Okay. Share it again, please.
Well, excuse me. My internet connection is
I see.
not the best.
Limited.
Yes. Okay. So, great. So, hello everyone. This afternoon I'd like to talk about this continuous time discrete state deterministic approach to chemical kinetics, which is a joint work with Gabor Lente. Now, I'd like to start the introduction to begin with this classical deterministic description of chemical reaction systems. So in this framework, the state variables are concentrations, so the system evolves in a continuous state space, and the dynamics are derived from the law of mass action, which leads to a system of ordinary differential equations. And each reaction contributes to the time evolution proportionally to its reaction rate and the stoichiometric change. Now, this approach works extremely well when the number of molecules is large. Now, the second classical framework is this stochastic approach, where the state variables are discrete molecule numbers rather than the continuous concentration. Now, this time, the system evolves as a continuous time markup chain where reactions occur randomly in time. So each reaction is associated with a propensity function, which determines the probability that a reaction occurs during a small time interval. So instead of tracking a single deterministic trajectory here, we describe the evolution of the probability distribution over all possible states. Now, this framework is particularly important for systems with small molecule numbers where the fluctuations strongly influence the whole dynamics. Now, these two descriptions are closely connected through this so-called Kurz theorem. So let's say we consider a stochastic reaction system in a volume denoted by this capital V, where the state is given by the molecule numbers. And if we divide the molecule counts by the volume, we obtain the corresponding concentration process. And so this Kurz theorem says that under suitable assumptions, as the system size tends to infinity, the stochastic process converges to the deterministic solution of the reaction rate equations. So when the number of molecules becomes very large, random fluctuation average out and the system behaves almost deterministically, which result explains why deterministic kinetics provides an excellent approximation for a macroscopic chemical system. Now, at the same time, this one also highlights an important limitation of the existing frameworks, because currently we have two extreme descriptions, the continuous deterministic models on one side and the discrete stochastic model on the other. So the motivation of our work is to investigate an intermediate regime. So a framework that preserves the discrete structure of molecular counts while describing their evolution in a deterministic way, thereby bridging the gap between these two classical approaches. Now, to construct a deterministic model with these discrete states, we use this newly introduced generalized concept of the reaction extent. So the reaction extent provides a qualitative measure of how far a given reaction has progressed over time. And instead of focusing directly on the concentration of the species, it describes the dynamics in terms of the cumulative progress of the reactions themselves. So for each reaction, the reaction extent is always defined as the time integral of the reaction rate multiplied by the system volume. And the reaction rate function describes how the rate of the reaction depends on the current concentrations, while the concentration vector contains the concentrations of all chemical species in the given system. However, in most applications, especially in our case right now, the volume is always assumed to be constant, which considerably simplifies this formulation. Another important feature of this concept is that the reaction extent is continuous in time, even though the underlying molecular changes are discrete in our new approach. So this reaction extent actually tells us how many times a reaction has effectively occurred during the given time interval. Now, classical kinetic models are usually species-centric, if I can say that, meaning that the concentration of chemical species are treated as the primary variables. Now, the reaction extent introduces a kind of different viewpoint, a reaction-centric description. So this time, the reactions themselves becomes the fundamental dynamical quantities. So once the reaction extents are known, the concentration of all species can be constructed using the stoichiometric information of the system. So this formulation is especially useful for complex reaction systems because it separates the network structure from the dynamical evolution. So our key idea behind this new discrete state deterministic approach is this following. So although the reaction extents evolve continuously in time, actual reaction events are assumed to occur only when a reaction extent reaches an integer value. Now, as a consequence, the numbers of molecules always remain integer valued, and the state of the system changes only in discrete jumps. So in this way, this new approach combines these two seemingly contradictory properties. So the dynamics are deterministic, but the state space remains discrete. So this one creates this intermediate framework between the classical deterministic and stochastic descriptions. Now, let me try to explain this, the core idea of this whole method. So first of all, we consider a general network consisting of n species and r reaction steps. And instead of focusing on concentration, we describe the system using a state vector, where each component represents the number of molecules as non-negative integers. So this approach already distinguishes our model from the classical deterministic kinetics, as the state space is discrete. Now, the structure of the network is represented by the stoichiometric matrix denoted by this capital S. And for each reaction J, we define a reaction rate function, which is non-negative and depends on the current state of the system. So these rates are typically given by mass action kinetics, meaning that they depend polynomially on the molecule numbers involved in the reaction. And more importantly, there is no randomness in these rates. So once the state is fixed, the reaction rates are fully determined. Now, the question here is how to define the time evolution of such a system consistently. So this is where the concept of the reaction extents I already explained becomes so essential. Because for each reaction J, we introduce a reaction extents by the Cj, which is defined as the time integral of the corresponding reaction rate. So this reaction extent measures how much reaction J has progressed up to time t. And since reaction rates are non-negative, each reaction extent is a continuous non-decreasing function of time. Now, obviously, this time, the volume, as I mentioned, is always considered to be constant. Now, the crucial idea here is that how we connect these continuous reaction rates to discrete reaction events. Now, a reaction event of type J is triggered whenever the corresponding reaction extent reaches an integer value. So this construction has several important consequences already. First of all, reactions occur at well-defined times, even though the reaction extents evolve continuously. The second is that each reaction event is deterministic, which means that given the current state, the rates, and the current value of the reaction extents, the timing of the next event is uniquely determined. So to each reaction, we assign the time at which its reaction extents reaches an integer value. Now, between events, the state remains constant while the extents of the reactions increase linearly. So when an event occurs, the state is updated according to the stoichiometry, which subsequently alters the reaction rates and the process continues. So as a result, the number of molecules remains an integer values and evolves in a stepwise manner similarly to the stochastic model, but this time without any given randomness. So the trajectory is entirely determined by the initial conditions. So this approach is particularly useful in this intermediate regime, where the deterministic models are not entirely reliable and the stochastic simulations could be unnecessarily complex and noisy. Now, let me illustrate this method on a classical, very well-known example, this Mihaly-Menten reaction, which is one of the most fundamental models in enzyme kinetics. And this reaction is actually, if I'm not mistaken, the most general one. So the mechanism here consists of three steps. The enzyme and the substrate bind to form this complex ES, and then this complex either dissociate back or it can produce the final product P while releasing the enzyme back. What makes this example particularly applicable is that the dynamics are really well understood already, so it provides a great benchmark for this new approach. Now, when we apply this discrete state deterministic approach to this Mihaly-Menten system, we can observe the time evolution of the molecule numbers. One of the first notable observations here is that the trajectories here are clearly stepwise. So the molecule numbers do not change continuously. Instead, they increase or decrease in these discrete jumps. So this behavior already reflects the fact that we are dealing with integer valued particle numbers. But at the very same time, this whole overall behavior of the system closely aligns with what we would expect from a classical deterministic or stochastic model. So the substrate is gradually consumed, the product accumulates, and the enzyme cycles between free and bound states. Now, this already brings us to an important point. Although the state space is decreed, the macroscopic behavior remains physically meaningful. So upon closer examination here, we can also see that the enzyme substrate complex is constantly forming and breaking apart, which generates this oscillatory pattern in the number of complexes, even though the overall system tends toward the product formation. So obviously, the time itself is always treated continuously, And while the system evolves continuously over time as well, the changes in the number of molecules occur only at specific even times, which are determined by this reaction extents. Now, in these slides, we can observe the reaction extents for each step. So each curve represents a specific step, and they increase continuously over time. So, however, the actual reaction events occur only when these curves reach an integer value. This provides already a clear interpretation. The reaction extent indicates how many times a given reaction has already taken place, but viewed in a continuous and cumulative manner. Now, in this next plot, I illustrated the fraction of each reaction extents representing individual reaction events. So in this plot, each spike corresponds to a single reaction event, and these different colors indicate different reaction channels. What is particularly important to notice here is that the sequence of these spikes is completely deterministic. And what I mean by that is that if we repeat the simulation under the same initial conditions, we will obtain exactly the very same pattern, which means that even though the trajectories may appear somewhat irregular or noisy, there is no randomness involved this time. So this example highlights one of the key strengths of this method. We preserve the discrete nature of chemical reactions while providing a fully deterministic description of the system. Now, the second example is a simple clock reaction. And clock reactions are very fascinating because they show a sudden and almost discontinuous change in the behavior after a specific delay. Now, the simplest set of reactions that displays this clock behavior consists of these two consecutive steps. And the second step involves a very fast reactions, while the species B serves as the clock species. Now, this means that the species B only appears after the reagent C has been completely consumed in the system. And it is also important that the initial concentration of this reagent A must be greater than that of reagent C, otherwise this clock species B would never appear and the system would fail to demonstrate this characteristic behavior of this clock reaction. Now, this result has a notable pattern. So as I mentioned, this clock species, the B, remains largely absent for an extended period of time and only appears suddenly after the species C is completely depleted, which especially can be seen here in this magnified part of the graph. Now, looking at the simulation results, we again observed this stepwise evolution in the number of molecules. So initially, the species C is gradually consumed, while the clock species remain nearly non-existent. And then once this C is fully exhausted, the clock species begin to accumulate very rapidly here. Now, this behavior closely resembles what we expected from this general clock reaction. And when we compare this outcome with the classical concentration-based description shown on the right-hand side figure, which comes from this article, we can find a strong agreement between the two. So although our model operates with small discrete molecule numbers, it still effectively captures the same macroscopic behavior. And in this slide, we can once again examine the reaction extents. So we observe that the reaction extent essentially saturates when species C is consumed, while the other continues to increase. Now, on the even-based visualization, here again we can see how the reaction events are distributed over time. So at first, both reactions are very active. However, once the species C is consumed, only the first reaction remains active. And this example is significant, I believe, that because it shows that even complex non-linear behavior with time delays can be effectively captured using this new discrete state deterministic approach. Now, let me introduce a slightly more complex example, this Ada-Stein reaction. And this model is one of the simplest biochemical systems that can exhibit multiple stationary states. Now, this one consists of 3 components and 6 reactions. And in this model, this X is produced through autocatalysis, while the other reaction describes its enzymatic degradation. When we examine the simulation results, so the changes in the molecule numbers as a function of time, we can see that the number of molecules fluctuates over time, ultimately settling into this fluctuating quasi-stationary state. But none of the components completely disappears, and the system remains stable. Now, at first glance, these trajectories may appear noisy, as if they were produced by a stochastic simulation. However, again, it is crucial to emphasize that this is not the case. So these observed fluctuations are the result of 2 main factors. First of all, the nonlinear reaction rates, and second, that the discrete updates of the molecule numbers. So because of the reactions happens very frequently in this system, the sequence of events becomes very dense, creating just the impression of that noise or fluctuations. Now we can also examine here the reaction extents, and we see a series of continuous piecewise linear functions, each corresponding to the reactions. Now I had to separate them since it was impossible to plot them in one figure. And on the even-based plot, what we can observe is a very dense pattern of these spikes, so the reaction events, which kind of says that the reactions are happening almost continuously in time. And despite the complexity of the system, this one remains completely predictable. So again, the same initial conditions always lead to the very same trajectory. So this example shows that this new approach, this discrete state deterministic approach, can also handle nonlinear systems with complex dynamics while still maintaining a deterministic structure. Now, in this example, I investigate this autocatalytic extinction model studied by Drummond and his co-workers. I left the citation on the next slide anyway. So this time the reaction system consists of an autocatalytic growth mechanism together an inversible depletion reaction or extinction step. Now this time the parameter, so the rate constant K1 is always 10 and the reverse reaction rate constant is 0.1. They are fixed throughout all the simulations, while the extinction parameter, the K2, is varied. Now, an important result of the paper is that the deterministic and the stochastic description predict a fundamentally different long-time behavior. So in the classical deterministic, continuous deterministic model, there exists a sharp threshold determined by the ratio of the reaction rates, and I mean by that the K1 and the K2. Yes. So the non-trivial steady state disappears in this continuous deterministic approach when the ratio of these K2 and K1 is greater or equal to 1. And according to this article, below this threshold, the deterministic system possesses a stable positive state, and the autocatalytic growth can persist indefinitely. Now, in contrast, the stochastic model always eventually reaches extinction because the state x0 is absorbing. So, however, the extinction time depends strongly on the parameter ratio. So when this parameter ratio is smaller than 1 in the stochastic description, the system may remain for a very long time in a metastable active state before fluctuation finally drive it to the extinction. So in this slide, I want to show you the molecular number trajectories obtained with these discrete state deterministic approximations. So in the left-hand side figure, now this one corresponds to the parameter ratio when the parameter so this ratio is smaller than 1. Actually, the K2 is 8.6 because from these points the extinction happens. So according to the deterministic model, the continuous one, this parameter regime should still support a stable active state and should not lead to extinction. However, in this discrete state deterministic approximation, extinction already appears from this point. Now, at the same time, the autocatalytic mechanisms remains highly effective before the extinction occurs. And this can be seen from the fact that the final amount of the Z produced is much larger than the initial amount of the species X. So the system first undergoes substantial amplification and only later collapses to extinction. And this behavior is qualitatively much closer to the stochastic picture described by Drummond, where extinction may occur after long transient amplification, even below the deterministic threshold. Now, this middle panel corresponds to the critical deterministic ratio when this ratio is exactly 1. So both race constants, the K1 and K2, are equal. And this is exactly the transition point identified in the continuous deterministic theory. Now here, the amplification becomes very limited. So the total amount of the species Z produced is only 1 molecule larger than the initial amount of X. And thus the system lies very close to a boundary between transient amplification and immediate extinction. And finally, on the right-hand side plot, now this one corresponds to the case where this ratio is greater than 1. Actually, the K2 is 15, if I'm not mistaken. Now, this is clearly inside the extinction regime predicted by the classical deterministic theory. So in this case, the depletion reaction dominates so strongly that extinction occurs rapidly, and the total amount of Z produced remains smaller than the initial amount of the X. Now, taken together, these results already suggest that the discrete state deterministic approximation shifts the onset of extinction below the classical deterministic threshold, and therefore reproduces several qualitative features usually associated with stochastic extinction dynamics. Now, the reaction extents provide a direct interpretation of how the competition between autocatalysis and the extinction changes across the three-parameter regime I already show you. So this time, the red curve corresponds to the forward autocatalytic step, the blue curve to the reverse reaction, and the green curve is the irreversible extinction reaction. Now, in this first regime, the ratio is smaller than 1. So this time, the forward autocatalytic extent initially dominates the dynamics. And this already explains why the system is able to generate far more Z molecules than the initial amount of the X. The autocatalytic reaction this time repeatedly amplifies the population before extinction eventually takes place. Now, this is particularly important because the classical deterministic theory would still predict persistence in this parameter region. So the discrete deterministic approach, what I apply, therefore, behaves more similarly to the stochastic description, where extinction remains possible below this deterministic threshold because of the influence of discreteness and absorbing states. Now, in this plot, the critical ratio is 1. So the autocatalytic and the extinction extents become nearly balanced. Only minimal net amplification occurs before the depletion reaction suppresses the dynamics. And for the third case scenario, the extinction extents dominates throughout the whole process, explaining why the system reaches extinction before substantial amplification can develop. So these plots clearly demonstrate how increasing the ratio of these two rate constants gradually suppresses autocatalytic growth and shifts the dynamics toward rapid extinction. And these final slides wants to visualize the actual discrete reaction events generated by this deterministic, this discrete state deterministic dynamics. So again, each vertical line represents a moment when a reaction extent reaches the next integer value, producing a discrete molecular event. So again, this left-hand side plot corresponds to the case where the ratio is smaller than 1, which is especially interesting again because it lies below the classical deterministic extinction threshold. So even in this regime, the discrete deterministic model still reaches extinction. However, the large number of autocatalytic reactions events show that the system spends a long time in this amplified active state before collapsing. Now, the critical ratio, where this ratio is 1, the balance between the amplification and extinction changes noticeably. So autocatalytic events become less dominant, and extinction occurs only limited growth, only after limited growth. And finally, on the third one, where this ratio is greater than 1, the irreversible extinction event dominates almost immediately, so the system rapidly approaches this extinction. Now, the most important conclusion here is that this new discrete state deterministic approach reproduces this extinction-like behavior even below the classical deterministic method. So I say that this suggests that discreteness alone already introduces mechanisms that are absent in the continuous deterministic description and that are actually attributed, usually attributed to stochasticity. And I also wanted to present some results of the Lotko-Watero reaction system using this new approach. So on the left panel, we consider the irreversible version of this system, while on the right hand side, all the reactions are taken to be reversible. Now, this irreversible model corresponds to the classical predator-prey type mechanism. So, X reproduces autocatalytically, the Y consumes the X and reproduces, and finally the Y decays. In the reversible formulation, each reaction can proceed in both directions, introducing additional feedback mechanism into the dynamics. Now, these lower figures show the time evolution of these molecule numbers. Now, let's see first the irreversible case. So for this system, we can observe this sustained oscillatory behavior. So the population of X and Y repeatedly rise and fall in a cyclic manner, similarly to the classical continuous Lotko-Watero equations. However, unlike the smooth trajectories of the continuous deterministic model, the oscillations here are staircase-like because the molecule numbers remain integer valued at all times, which can hardly be seen in this small version of the plot, but closely you can see that. So let's see it in contrast the reversible system, which behaves obviously very differently. So instead of sustained oscillations, the trajectories gradually approach a kind of small oscillatory neighborhood around an apparent equilibrium state. So the discrete nature of the dynamics becomes especially visible here. So here, the system cannot converge to a perfectly stationary continuous equilibrium because the molecule numbers remain integers. So as a result, the system settles into a small persistent discrete oscillation around an equilibrium point. And this is one of the characteristic effects introduced by this new discrete state deterministic approach, because I believe that this time these continuous equilibria are replaced by small deterministic fluctuations generated purely by the discreteness. And this slide shows the corresponding phase portraits of these two systems. So for the irreversible Lotko-Watero model, here, the trajectory forms a large closed orbit. And this behavior again closely resembles the periodic trajectories of the classical continuous Lotko-Watero equations. But this time, the system repeatedly cycles through phases of prey growth and predator growth and prey depletion and predator decline, etc. And here, this one indicates the direction of the evolution along this orbit. So, although the trajectory resembles the continuous deterministic solution, we have an important difference here. The orbit is composed of discrete jumps rather than a perfectly smooth curve. Does this model preserve the qualitative oscillatory structure of the classical system while maintaining integer valued molecular populations? Now, about the reversible system, this one exhibits a different behavior because this time the trajectory spirals inward a small discrete invariant region near the equilibrium state. Now, in the continuous deterministic setting, these reversible reactions would typically produce convergence toward a stable steady state. But in this discrete state deterministic description, the exact convergence I believe, is impossible because the state space is discrete. So instead, the system evolves into a small cyclic pattern around this equilibrium. So the phase portrait here can illustrate how discreteness modified the long time behavior. So continuous equilibria become these small deterministic oscillatory attractors. And this phenomenon is especially important because it appears without any stochastic fluctuations. So this time, the oscillations are generally generated purely by the interaction between deterministic evolution and discrete state changes. And finally, we examine the reaction extents associated with the Lotka-Volterra dynamics. So this one again corresponds to the irreversible system, this left-hand side plot. The reaction extents increases in almost periodic staircase-like manner, reflecting the cyclic manner observed previously in the molecule number changes. And each rapid increase correspond to a phase where the associated reaction becomes dominant. And because the system undergoes these repeated oscillations or reaction extents continue to grow infinitely over time. Now, the periodic solution of the curves demonstrate that the reaction network repeatedly passes through similar dynamical phases. The right-hand side figure corresponds to the reversible system, which obviously have a different behavior. Initially, several reaction extents grow rapidly as the system relaxes toward equilibrium. And later, the growth becomes much slower and much more balanced between the forward and the reverse reactions. And this reflects the fact that the reversible system approaches a near equilibrium regime where opposite reactions almost compensate each other. Nevertheless, these reaction extents never become exactly constant because the system continues to perform small discrete oscillation around this equilibrium. Another important observation is that the forward and the backward reaction extents remain separated by small but persistent differences. And these differences are precisely what maintain these residual oscillatory dynamics in this discrete state deterministic approach. So overall, these results can show us that this new approach successfully preserves many qualitative features of the classical Lotka-Volterra dynamics, including the oscillation, the phase space structures, and equilibrium behavior, while simultaneously incorporating the fundamentally discrete nature of the molecular counts. And before I conclude this whole, let me give you an important structural property of this new model. So what this slide tries to tell us in simple terms is that the system can only evolve within a certain restricted set of states that is determined by the reaction system itself. In other words, what I already tried to tell you, once we fix the initial conditions, the system cannot move arbitrarily in the state space, and it is constrained by the stoichiometry of the reactions, which means that all changes in molecule numbers must be consistent with the reaction steps. And the system can only reach states that are accessible through the combination of these reactions. And this is important because this one can assure that the model is not only mathematically consistent, but it can also be physically meaningful. And my final result here try to demonstrate the existence and uniqueness of these trajectories. So given certain assumptions, especially when I mean that the feasibility of the reactions and the bounded reaction rate, the model ensures unique time evolution for all the time t. The other thing is important to note here is that when reaction rates are not bounded, so infinitely many reaction events can occur in a finite amount of time, then the meaning this theorem does not apply to such cases. And additionally, I also would like to give a small intuitive interpretation related to the concept of the reaction extents, which I believe can clarify this numerical implementation. So while the number of molecules is discrete, the reaction extents are continuous as they are defined as the integrals of the piecewise constants of the rate functions. Consequently, although they are continuous, they are not differentiable everywhere, so there are discontinuities wherever the reaction rates change. And the main reason why I show you the fraction of the reaction extents in some slides is that in practice, we do not necessarily need to track the entire reaction extents, especially because we can save some computational time. And it is also sufficient to monitor its fractional parts. So register an event each time the extent increases by exactly one. Because between these states, the system state remains unchanged, and it evolves only in relation to the reaction extents. So when an integer threshold is reached, we update the molecule numbers and then continue from these new states and etc., etc. So this interpretation can highlight a key idea here. So while the dynamics are continuous in time, all physically relevant changes occur in a discrete, well-defined steps. And thank you.